So in today's webinar, Jamie and I are talking about vectorization, some basics and approach, and also how to apply it to particular CVA aggregation codes. I guess pretty much all of you are well aware about Moore's law, which says that number of transistors on the die doubles each and every 18 months or so. And surprisingly, that law is still well in the life. So we are getting more and more transistors state on a die. But on the other hand, you may have noticed that frequency-wise, clock speeds are pretty flat from about 1005. And that means that those transistors are mostly translate into high levels of parallelism rather than increased single-threaded performance, although modest increase in single-threaded performance still takes place due to market architectural enhancements. If you look at recent Intel's processors, you could see that if you compare to first Intel Xeon 64-bit one released in 2004, course has risen from 1 to 28 in most recent Intel Xeon Scalable processor, and in Xeon 5 family it's even more, up to 72 cores. And another way of parallelism is SIMD, single instruction multiple data, which is obviously vector operations, and vector operations has also increased in capacities. So in the past it was a 128-bit instruction set capable of operating on either 2 double precision values at once or 4 single precision values. And with modern architectures, this is AVX512 instruction set with 512-bit vectors. And those vectors allow handling either 16 single precision or 8 double precision values by one instruction. So as I said, single threaded performance is rising very modestly. And this is why modern software must be built for parallelism to get efficient performance from modern CPUs. And this is a combination of both threading and vectorization that provides the most dramatic performance gain. So if you just multiply numbers for most recent top bin Intel Xeon Platinum processor, which are 28 cores by 16 single precision values, so in single precision you can get 448x speed up, which is obviously really massive. And it's not just theoretical number. To illustrate what is realistically achievable, I put a graph at the right-hand side of this slide, highlighting how binary option pricing performance behave on a different set of different processes, starting from single-threaded non-vectorized versions, non-vectorized version at the bottom, then single-threaded vector version in a red color, then multi-threaded non-vectorized version in gray, and finally parallel and vectorized version combined, which is in yellow. So you could see a really dramatic performance increase measured in hundreds X. So this is really realistic for at least for certain workloads. So I guess you're pretty much aware about vectorization. So it's simple. It's pretty much the same instruction set operating on scalar versions, scalar data, just doing operations on multiple data packed into vector register. So instead of doing instruction on one element, it does instruction on a number of elements. So as I said, for 512 bit registers, it could be 8 double precision or 16 single precision values. And what is interesting is that for majority of those instructions, if you compare scalar versus vector, latency and throughput are pretty much the same. And this means that that 8x or 16x improvements are quite realistic. Unfortunately, not all kind of code is vectorizable. So when we talk about vectorization, it's about multiple data processing. And this means that we need to have this multiple data. So normally we would be talking about a loop operating on, let's say, an array. There is a number of issues that either prevent or vectorization or make it harder for compiler or less efficient. So the showstopper problem is true dependency or read after write dependency. So this is when a particular element, the value of which we are to calculate, depends on value of previous element. So that is true dependency, and obviously we cannot simultaneously calculate a of I and a of I minus 1. So this is a real showstopper in vectorization, and parallelism also is not possible in principle. The second issue that you may hit working on vectorization is pointer aliasing. So when you pass pointers, let's say into function, and then operate on pointer values through pointer arithmetic or any other approach, compiler by default would assume that those pointers may overlap in memory, and that would mean a true dependency. There are means to provide compiler a hint, and I will be talking about it later. Another problem is indirect memory access. So it's not a showstopper. Compiler normally would be able to vectorize this kind of code, but that vectorization comes with certain overhead because data needs to be gathered and packed into vector registers and then possibly scattered again from vector registers to various locations in memory. And that is not something free. That takes some time to do. And finally, there is a bunch of other reasons why vectorization may be either complicated or come with overhead. And we put them under non-straight line code umbrella here. And those situations include function calls inside loop body, conditional statements, unknown iteration, number of iterations, and some others. So in many cases, we are not showstoppers, and compiler could do vectorization for you, but not always, and sometimes compiler would need your help as a developer. In terms of approach, a set of options from lower level, like assembler code or coding in intrinsics. And intrinsics are basically like C function calls implementing more SIMD intrinsic classes. So those are low-level coding, providing full control over vectorization, but they may have some restrictions in terms of portability because they may be linked to a particular instruction set, so it may not run on, let's say, earlier generations of processors, for example, or may not be portable. And higher-level approaches start with performance libraries. I guess many of you have heard about Intel's math kernel library. And libraries are typically well optimized, and they have vectorized code and implementations for different options to compiler, saying that code needs to be vectorized for a particular instruction set, and compiler would do job for you. So you don't have to do any change of code, just compiler option. Not be able to vectorize loops due to a number of reasons. Some of them I mentioned on previous slide. And in these cases, you may need to apply some auto-vectorizer. Please vectorize this particular function, override your heuristic and vectorize, if possible. These kind of hints do not guarantee vectorization. They are just, and there is more explicit, there is a set of more explicit means or user-mandated vector programming. So some are, another implementation is Intel CVA on following slides. What are those? And six-step approach. So first step would be to measure baseline performance of the code you have at the moment. Then determine particular hotspots and check compiler reports and determine loop candidates. I mean, those loops that are either not vectorized or not particularly efficiently vectorized. So when you would need to do certain analysis to understand what are the reasons for either inefficiency or absence of vectorization, and then go and implement vectorization when possible. So when you just repeat this cycle to work on next level of hotspots and so on and so forth until performance is acceptable or there is nothing else to do. So at first step, when you measure baseline performance, you have to use a release build with proper compiler options, because it doesn't make sense to start with debug build when nothing is optimized. To make compiler generate vectorized code, you need to specify architecture-specific option. So for most recent architecture, this is Xcore-AVX512. For earlier architectures, it's Xcore AVX2, AVX, and some SSE options. If you need to generate code for a particular computer on which you are doing a build, you can use -X host option, so building for current architecture. I would always recommend using O3, high-level optimizer option, or at least O2, together with vectorization options, because that option makes compiler to apply some advanced optimizations, do loop transformations and stuff. So that could help a lot in terms of vectorization or vectorization efficiency. And that build would be a good baseline to compare to when you apply vectorization, further vectorization on hotspots that were not vectorized or not vectorized efficiently. To determine hotspots, it has really wide functionality, addressing pretty much all possible issues from parallelism and vectorization and performance on the top of different types of CPUs. But for determining hotspots, you just need plain hotspot or advanced hotspots analysis. And what you get is the top is hotspot view, and you can see process, thread, module, function, and loop. That selected loop at line 206 in the this particular loop is from the top. So you could see clearly what are the main loops, main contributors to time consumption or CPU usage, and so on and so forth. You can double click on each of those, well, not each, functions or loops in that table, and you'll get a source view as the picture at the bottom of this slide shows. And in source view, you would see a source file with time spent in Unity to open and disassembly view. And you can, if you are a little bit aware about assembly instructions. So for that particular loop, I could see from disassembly that this is a vectorized code, because it uses instructions with PD at the end. And PD means packed double. So I know that that code operates on double precision values and in a vector way, because it's packed double. And I could see here, I clearly see that data pretty well performing loop. So at this stage, you need to determine particular compiler report, which is very helpful. And to generate that, you can use a set of options that are provided on this slide. And there could be a couple of outcomes. So either loop vectorized or not vectorized. For not vectorized loops, compiler would provide an advice. Why, I mean, not advice, but provide information why that particular loop was not vectorized. So in this particular case, you could see that remark is that there is vector dependence, assumed anti-dependence between counter, which are located in line 15 of this code, column 3, and the same variable at line 18, column 4. And for vectorized loops, a compiler provides information that particular loop is vectorized, and a lot more information. Actually, I stripped a lot of it, but what I'd like to show is that compiler also estimates potential speed up out of vectorization. So in these cases, it is 3.5x. compiler obviously knows very well instructions latencies and throughput, so that estimation is pretty accurate, but it's made on the assumption that data is supplied from L1 cache. And L1 cache is the closest location with highest bandwidth and lowest latency. So in case if you operate on data that is larger than L1 cache, you would see lower speedups because data delivery takes some time. But still, vectorization is useful option, and in the majority of cases you would see decent speedups, depending on data locality. Another useful tool that helps Intel's Vector Advisor, which is a part of Advisor to Vitune. It's a list of loops. You can see in front of every loop, you could see some vector issues captured by this tool. So explanations, what is inefficient. You could see time spent in that particular loop and break down by total time, if it's nested loop, and the self time. You see if it's vectorized or scalar loop. If no vectorization, it would also explain why not. That tool AVX in that case. And also efficiency of this particular loop. And efficiency means how much gain you are getting. The next actually value in that table is gain. And as you can see for the top loop, it's 2.19x or double precision values. And that means that you are getting 2.19x out of 4 possible. One more useful thing, which is not directly maybe related to vectorization, is a plus. That is really useful when you apply parallelization and vectorization, because it shows you a hierarchy of nested apply parallelism and where to apply vectorization. You can double click on any loop in the list, and you'll see a number of. So one particular type of interest is why no vectorization if the loop is not vectorized. So you'll see your code, and the tool provides recommendations, and also providing you a list of directives that may help you to force compiler to do certain action or any other kind of advice. So the next step is to apply. So let me start from pragma options or explicit vectorization approach. So pragma SIMD, which is now considered outdated, and new compiler will also only support pragma OpenMP SIMD, which is a part of OpenMP 4 and higher standard. This is a directive to compiler, and whatever the cost, whatever heuristic, whatever the dependency, which means that compiler will vectorize that loop. So as a developer, you need to be very careful. You need to be really sure that there is no true dependencies. In this case, if it's transparent for you, you can will be vectorized for sure. For example, there may be particular lines of code that couldn't be vectorized in principle due to kind of true dependency on our issues. And in such cases, you can apply pragma SIMD off for a particular line of code or particular block of lines. And that pragma would switch vectorization off for that particular block. It always comes with certain overhead, but still, in many cases, you would see significant speedups, even with. That is worth mentioning is that is when there is any reduction variables, like in a right piece of code at the bottom, and particular variable that accumulates a result. Imply restrict keyword, and you also would need restrict compiler option. And that keyword tells compiler that those pointers never overlap. Again, responsibility for code correctness is on you in this case. Function calls could be quite often vectorized by compilers. I'm talking about function calls in a loop body that is subject to vectorization. And in this case, compiler would inline vectorization. But sometimes compiler wouldn't do that for a number of reasons due to some heuristics or any other things.
So you can apply a keyword like a decal spec vector on Windows or attribute vector, I believe. Forces compiler to generate at least two options for the loop, one scalar and the other vector. And depending on compiler options, it could be more than one option if you generate code for multiple architectures. And so multiple vector options would be available. It's quite important to, if you use pointers in a function that needs to be vectorized, it makes a lot of sense to specify how data index is accessed. So the best possible case is when access to the pointer is uniform, meaning that one by one, data elements would be sequential. In this particular case, vector function would be vectorized in the any overhead or any gather and scatter type of instructions used. If you don't specify any of those, compiler it never knows if data would be accessed sequentially or with jumps over memory. And that would cause quite an overhead. You just need to repeat this step again and again as soon as your major loops are vectorized and you are satisfied with performance. Okay, so now it's Jamie's turn to talk about applying vectorization to CVA aggregation.
Thank you, Evgueny. That's a nice introduction and overview of the general topic. It's nice to look at specific examples, and so we're going to take an example from the finance domain. There's actually lots of good candidates. If you're a quant, there's good candidates in finance for vectorization of the code. If you're dealing with, say, matrix transformations, linear algebra, and then curves are vectors or surfaces. So there's lots of opportunities to try to implement this and improve the performance of your code. We're going to take a nice example, something that Quantifi has been working on vectorization of fairly recently, and we've had a lot of success with. That's the aggregation of CVA. CVA, for those who are not so familiar with this topic, CVA stands for credit value adjustment. It's an adjustment, it's a risk measure that's a dollar value adjustment to the mark-to-market of the portfolio to account for the risk of counterparty default. So we take the mark-to-market and we can subtract the CVA, we'll have a credit adjusted mark-to-market portfolio value. So how do we calculate it? Usually by Monte Carlo simulation, simulate the exposures over a series of dates into the future, series of time steps, and run many sample simulations along a time series, and evaluate the portfolio and build a distribution of exposures for the portfolio. So when you run this simulation, what you end up with is a multi-dimensional array, a number of sample paths, values for each trade along the sequence of dates that you simulated. And to compute the CVA, we're going to try to reduce that multi-dimensional array down to a single number. So we aggregate across each dimension, across the trades, and then across the paths, across the dates, until we've reduced down to a single number. Okay, so let's have a look at the first step. So the first step is to aggregate across trades. This is what we call netting, because usually a pair of trading parties will have a legal agreement that allows all the exposures, or at least exposures of a certain product type or something like that, to be netted out during the closeout if a counterparty defaults. So that means that a positive exposure and a negative exposure can just be added together. So it ends up meaning that when we're doing the maths, it's very simple. You just add all the individual trade exposures together. So our first little bit of code here is a nested loop. we loop over each of the trades, each of the paths, and each date, and simply just add up the trade values for each path and date into a net total for the portfolio, or all the trades for that counterparty. Now, the inner loop, let's remember, when you're doing vectorization, it's almost always the inner loop that is the one that gets vectorized. So we're looking at that inner loop looping over dates, and that looks like a very good candidate for vectorization. So what you could do is, as we saw, you can run the compiler report, or we can look in Vector Advisor and see whether the compiler has managed to work out that this loop can be vectorized already. If not, we might need to give some help with compiler hint, that sort of thing. Maybe PragmaSimD, something like that, to ensure that the compiler knows there's no dependencies there between those two vectors, and it can go ahead and implement vectorization. So that's nice, probably a nice simple example, because the net exposures and the trade exposures, it's the same dimensionality, so the same length arrays, and you're just stepping over one by one through each element in the array, so it's sequential, and so you can do one at a time, a scalar operation, or we can do however many of those floating point values fit into the vector register, do those additions all together concurrently with the vector operations. Slightly more tricky is the next extension of the above netting. Sometimes you may want to aggregate onto a different time grid. So in that case, we'd use interpolation. So we want to interpolate the trade values from the original dates onto some dates in between, some new set of dates. In this example code, we're using linear interpolation. I think we've got quite a few quants in the registered attendees, so most of you will know what linear interpolation is. It's just a weighted sum of the two surrounding values. So we're doing trade exposures at index A times a weight alpha, trade exposures index B times a weight beta. And the complexity that's introduced here is that with those A index and B index, we're using indirect indexation into the arrays. So immediately we've made things a little bit harder for the compiler, and because the elements that we're adding or multiplying them might not be immediately sequential in memory, there might need to be some packing of the array into the vector register before the vector operations can occur. But you can still vectorize this in a loop. You'll be slightly less efficient than probably the previous example, but it's certainly still worth doing. So we net up over the first dimension, and we reduce down to a two-dimensional array by paths and dates. We've got net exposures by path and date, and the next step that we may need to do is to calculate the collateral. So counterparties may choose to reduce their exposure to each other through the requirement to post collateral if exposures exceed some certain threshold. There's a lot of different ways that collateral can work. We're looking at a very simplified example here just for didactic purposes. So in this example, if the net exposure exceeds the threshold K, then we assume collateral gets posted. And so the variation margin, the margin amount, is just going to be the excess of exposure above, yes, it's going to be the excess exposure above K. So net exposure minus K, or 0 if net exposure is less. So we do a max operation. And max is a nice simple function. Typically your compiler will have that in the compiler library, and it's vectorized, the vectorized version available. So we give a list in the white paper of a bunch of built-in vectorizable functions. So max net exposure minus K, that operation is going to be perfectly vectorizable. And again, the same process, you probably have a look at the compiler report to see if it had been vectorized. If not, then you can help the compiler with a compiler hint like a pragma-SIMD. After computing the margin amount or the collateral amount, now we're going to compute a collateralized exposure, which is simply the original exposure minus however much collateral was posted, because the collateral reduces the exposure. So we're taking net exposure minus variation margin, and then the max there is simply to say, if the exposure is negative, we're not interested. We're only interested in positive exposures. So we're just flooring at 0. But again, another max operator, so it's very similar to the previous loop and certainly vectorizable. So now we come to the first sort of real risk measure here, with something that you might look at in a report. This is expected exposure, and that's essentially the average exposure. So we've done a simulation and simulated a large number of paths, say 5,000 or somewhere around that, thousands of paths, and we're going to aggregate up and take the average exposure for each date. So just summing up and then dividing by the path count in the simplest case. That's a very simple average. So again, it's the inner loop of the first nested loop there that's going to be parallelized. So, sorry, excuse me, going to be vectorized. So, and it looks straightforward again. The two arrays there, we're going over two arrays of the same size sequentially and just adding the values. So we go through the same process and allow the compiler to vectorize that. And the second loop is division by a constant, so it should also be vectorizable. And then we come with EE, which is a value for each date, the expected exposure for each date. And finally, having computed an exposure, an expected exposure for each date, we're going to integrate over time. So summing up the exposure times the probability of default for that time period, and times the loss given default, which is just an assumption about what percentage of the original value will be lost. You know, this usually creditors get some portion of the amount owed returned to in the event of a default. So we make some assumption about the loss given default, but otherwise this is all straightforward. Exposure times default probability times LGD. All these arrays are, again, same size, and you're sequentially just multiplying each element. So that should be vectorizable. And then the final point there is that the CVA is a single number, so that it's not a regular SIMD aggregation. You'd have to mark that slightly differently. It's a SIMD reduction, so there's a pragma SIMD reduction, and then you'd identify CVA as the variable. But again, nice and easy to vectorize. So CVA is really a great example of some straightforward aggregation over arrays of data that is extremely suitable for vectorization. Okay, so that's our example, and we're going to take some questions.
Great. Well, thank you, Jamie, and thank you, Evgueny. So we'll now move on to the Q&A session, and during the course of the webinar, we've had a few questions come in, so we'll try and answer as many as we can. So the first one I've got here is, does Quantifi use Intel, and if so, how? I guess, Jamie, that would be one for yourself.
Sure, thanks, Secretary. So, yes, we do, of course. We've been using into a parallel studio which integrates into Visual Studio. We're mostly a Microsoft shop, so it's really nice to have a tool that integrates so well. And it's a and Evgueny shown some of the screenshots of what it's capable of. It's really unparalleled, I think, in terms of the sophistication of what you can do when you're coming to really drill down into and optimize a piece of code and try to vectorize it, and also really fantastic for multi-threading, parallelization as well. I mean, I should have mentioned maybe when we're going through those loops, when you have a multiple nested loop like that, typically we'd be trying to vectorize the inner loop and then look for independent sets of data that are in the outer loops and parallelize the outer loop as well. And so, you know, the Intel tools are fantastic at both of those things.
Great, thanks. So another question, what vectorization option do I apply if I do not know in advance what platform the application will be running? Evgueny, maybe that's one you could answer?
Yeah, actually, you can combine as many options for particular architectures or instruction sets as you want. Compiler in this case will generate multiple versions of loops. So you'll get somewhat larger binary, but usually not by very much, because not each and every loop is vectorized, and there are not loopy code and so on. And also you could generate a generic option that would run on any x86 architectures. And when you generate this kind of application with support of multiple architectures inside, a particular version of a loop will be taken at runtime. So underlying architecture is checked by application, and then proper loop is taken with virtually zero overhead. So just combine multiple architectural options like XSSE 4.1, Xcore AVX2, Xcore AVX512 in a row, and the compiler will generate a number of versions of loops for particular instruction set.
Okay, I think there's another one here for you, Evgueny. Are there ways to improve vectorization performance if you use non-unit stride access data?
So generally speaking, non-unit stride access causes overheads because, as I said, data needs to be gathered or scattered then, and that doesn't come free. And it doesn't come free from a couple of standpoints. First is due to instructions involved in doing operations, and secondly, when you access data non-sequentially, you would need to load more cache lines. And of course, I mean, cache bandwidth considerations also contribute to performance here. So ideally, you would like to just change layout of data, reorganize data access to make it sequential. One of typical examples that appears in that cases is changing array of structures to structure of arrays. If you, for example, access particular field of number of structures, you better use a structure of arrays instead of array of structures. But it really depends on your code, and in many cases you can't really do anything with non-sequential access. It's a matter of a problem quite often. But what I'd like to mention is that with new AVX512 instruction set, Intel introduced a lot more flexibility for data manipulation, and it delivers much better efficiency nowadays for such kind of data access patterns.
Okay, thanks. And so another one for you, Jamie, I think. What method does Quantifi use to implement vectorization in production code? Pragmas?
Right. Yeah. I think the question is we looked at a number of methods, or Evgueny did, of increasing sort of sophistication in one of the slides where you can sort of just let the compiler do stuff. You can add pragmas and hints for the compiler through to SIMD instructions and all the way down to very sophisticated line by line SIMD specialized code. So it's definitely still a subject of active research here at Quantifi. We're always trying to make things faster, but we've found that so far, just by analyzing the code and structuring it well, and we can usually get away with just giving the compiler hints to pragma SIMDs. It's really quite a powerful method, and you can get a lot out of that. So that's where we're at the moment. But certainly, we're going to keep working on this. So we may hit problems where we need to do something more sophisticated.
Great. Okay. I'm afraid that's all we have time for today. Please note we do have a related white paper available on our website. You can go to www.quantifisolutions.com/whitepapers, and a recording of this webinar will also be available in the coming days. And I'd just like to finish off by thanking Jamie and Evgueny for presenting today's webinar, and thank you all for listening, and I hope you enjoyed the webinar today. Thank you.